Thank you for the introduction, Jacqueline. So I think this talk is going to be a little bit different from the others in the session, in the sense that I'm considering here a very simple model. We've seen very models which have very complicated features during the day-to-day. This talk is going to be about a very simple model, but I'm going to ask some questions whose answer is not trivial at all, and whose answer turns out to be very delicate and make some links with interesting domains of mathematics. So this talk is based on a series of joint works with a few collaborators, whose list is given here. And in this talk, so I'm going to start with an introduction, just introducing the problem. Then I'm going to, so it's a problem on linear time delay systems, and contrary to many other talks from today, I'm going to study it from a spectral point of view. And so I'm going just to recall the main facts of the spectral analysis of time delay systems that are interesting to me before getting to the kernel of my talk, which is this interesting property called multiplicity-induced-dominancy, and when with extensions of this property. Okay, so the system I'm interested in this talk is this very simple equation here. The unknown is a scalar, y of t. So y of t is my instantaneous state, and I have an equation with a single constant delay tau, which is of course positive. So it's an equation of order n. I have here n derivatives in the delayed part, and I have at most n derivatives in the delayed part. Sorry, there's the non-delayed part, and at the most n derivatives here in the delayed part. I say at most because some of these coefficients may be zero. So I have here my system that is determined by these coefficients a0 until an minus 1, alpha 0 until alpha n, which I assume to be real. And during this whole talk, I'm going to make some differences between the retarded case, which is when alpha 0 is equal to n and the highest order of derivation only appears here, and the neutral case, which is when alpha 0 is different from 0, and so both of these terms here appear, and the highest order of derivation appears without delay and with delay. So when you look at a system like this, it's a linear system, it's a linear equation, it's quite simple. And one of the questions we may ask is the system stable, and can I compute its stability algorithmically from its parameters? So if I have these numbers, a0 until an minus 1, alpha 0 until alpha n, and the delay tau, can I implement some algorithm that will take these numbers and give as an answer if the system is stable or not, for instance? And the other question that comes with this one is, let's assume that you have some choice of these coefficients, which may happen in some situations. If we can choose some of these coefficients, can we choose them in order to stabilize the system? Can we choose these coefficients in order to ensure that with our choice, the system is exponentially stable and possibly with a prescribed rate? Okay, so the motivation for me is from the point of view of control theory. So in control theory, you usually have a differential equation or a system of differential equations in which you have a certain function here, a control that you can choose. So you can choose this function u, and the question is, we want to choose this function u in order to achieve a certain goal. So for instance, I may want to reach a certain target state. So I may want to choose this goal such that my solution after some time is equal to a target state. Or I may want to stabilize the system, meaning that I may want to choose this u in such a way that with my choice, solutions of the system converge to 0 or to a prescribed state. And a very classical technique for that is to do what we call linear feedback stabilization. So linear because this is a linear function, feedback because we're using information on the state y to do the stabilization. So we choose u as a linear combination of the function y and its derivatives at time t in order to stabilize the system. And so we get that with this choice of u, the solution y will behave as the solution of this system here. And you see that this amounts essentially to choosing the coefficients of the system, because in this way I can modify A0, A1 until AN minus 1 by choosing appropriately my alpha 0, alpha 1, and so on. But the problem is that we can try to do this in practice. So we can try to put a sensor somewhere that will measure y and that will measure its derivative and so on. And we can use the information of the sensor to do the computation of these things and then compute u and then plug this u into the system. This can be done in physical systems. But the problem is that all of this procedure takes some time. And so there's a delay, meaning that I'll measure y of t, I'll measure y prime, and so on. And then I will multiply by all of these, I'll take the sum, I'll change the sign. And then when I finally compute u of t, some time will have elapsed. And so at time t, this computation will have been done with y of a certain past value. And so that's why delays may appear in these equations. And that's why it's interesting to study these equations when we have some choices of the coefficients here, which comes from this linear feedback stabilization problem that we have in control theory. Okay, so what happens? So let me go back to the questions that I have asked concerning stability and stabilization. What happens if you have no delays? So what happens if I have just an equation like this? So if I have just an equation like this, we can study it from a spectral point of view. And its spectrum is just the set of roots of a characteristic polynomial. So the set of roots of a polynomial function here, whose coefficients are the coefficients of the equation. And we have Hooft-Hurwitz criterion, which is an algorithm to determine whether P has all its complex roots in the open left plane, which is equivalent to saying that this system here is exponentially stable. So this algorithm is just taking as inputs the values of A0 until AN minus 1, is doing some computations, and in a finite number of steps, it's going to say, yes, the system is stable, or no, the system is not stable. So we do have this characterization of stability based only on the information of the coefficients. And for the pole placement point of view, the idea is that if I take any set of n complex numbers that appear in complex conjugate pairs, so if I take one complex number, I must take also its complex conjugate if it's not real, I can always choose my coefficients in such a way that the roots of P are exactly these roots. So this means that if I have the choice of all of these coefficients, I can just choose the roots of this polynomial where I want. And so in particular, I can choose them to have negative row part, and then I can choose them to stabilize the system. So we can achieve this if you do, for instance, a linear feedback stabilization in order to modify these coefficients by adding some alphas here, as I said in my previous slide. So this means that the two questions that I had asked have some very simple answers in the delay-free situation, but the situation is much harder when we have delays. So what happens when you have delays? So when we have delays, I have this equation here that I'm considering, and its characteristic function is now given by this. So it's a polynomial here, which comes from this part of the equation. And here I also have a polynomial, but because of the delay, this polynomial is multiplied by this exponential of minus s tau here. There are very classical facts of these kind of functions. So the first one is that S in the finite dimensional setting, the roots of this equation determine the asymptotic behavior. And what I'm interested in is exponential stability. And this is equivalent to saying that all roots are less than or equal to some negative number here. So there exists a certain gamma such that all roots are less than or equal to minus gamma. And it can also be shown that, except for the trivial situation where we have no delay, this function here has infinitely many roots. And now we have difficulties because we cannot answer the previous questions that we could answer in the case of systems without delay, because there is no easy generalization, or at least no non-easy generalization of Hooft-Hurwitz criterion, meaning that we do not know any algorithm that you just take these values alpha, these values a, and the delay tau, and you'll say, yes, the system is stable, or no, the system is not stable. And since we have infinitely many roots here, we cannot do full pole placement. You cannot take an infinite sequence of complex numbers appearing complex conjugate pairs and choose the values of the coefficients in order to have those values as solutions, as zeros of my characteristic functions, simply because I have here only finitely many coefficients, but I will need to assign infinitely many roots. So these are the main difficulties when we go to this time delay point of view. Now this characteristic function here that I've just presented you, it is actually somehow very special function called a quasi-polynomial. A quasi-polynomial can be defined as a function that can be written as a finite sum of polynomials multiplied by exponentials. Okay, so I have here some exponentials. I have here, I just ordered here for simplicity. I have these polynomials, and these polynomials are just, I can always assume that there are no zero, otherwise I just don't count them in the sum. And there's a very interesting result, which was proved in the beginning of the 1920s, on the location of the roots of these quasi-polynomials. So this result says the following thing. Consider this number here, d. d is what? So here we have the sum of n plus 1 terms from 0 to n. So d is the number of terms minus 1, which is n, plus the sum of the degrees of all the polynomials that appear here. Okay? So if I consider an horizontal strip in the complex plane, so if I consider the set of all complex values which are between alpha and beta, and I count the number of roots of this function that appear in this horizontal strip. What this result tells me is that I have a bound. This number of roots is between these two things here. This is the same term here, but here with minus d and here with plus d. And this term depends thus on this number d, this integer d, which I'm going to call from now on the degree of the quasi-polynomial. It depends on the size of the strip, and it depends on the difference Rn minus R0, so the largest difference of the terms appear in the exponentials, which is, when you have delays, this is just the largest delay appearing in the system. So we have this bound on the number of roots that depends on the largest delay, on the size of the horizontal strip in the complex plane I'm looking at, and on the integer d. So for instance, what you can also see from this bound is that if I have a region here, I take an horizontal strip in the complex plane that is large enough, if it's large, so that this whole number here is strictly positive. So if I choose beta minus alpha to be large enough so that this number is positive, then necessarily I know that I have a root here because this m is going to be greater than or equal to a positive number. Since it's an integer, it's going to be at least 1. Okay, so if beta minus alpha is large enough, I know I have at least one root here. And on the other hand, if beta minus alpha is small enough so that this term here is strictly less than 1, then m being less than or equal to d plus d is going to be the same as m being less than or equal to d. And so this means that I have at most d roots in an horizontal strip of size small enough. Okay, so this gives me some information on the location of the roots in horizontal strips. And since these roots are counted according to their multiplicity, this gives us a very interesting corollary, which is the one I'm going to talk about, which is that any root of delta has multiplicity at most d. Because if you take a root, for instance, let's say that you have a root here, you take a very small strip containing this root, and you know by this bound that the number of roots here is at most d. So since this number is counted according to multiplicity, we know that here I'll have at most d roots. Okay, so I've been talking now about multiple roots. And before I was talking about stability, and stability is determined by the location of the spectrum, and it can be seen as determined by the location of the rightmost root of the spectrum, that is the root with the largest real part in the spectrum, which I'm going to call a dominant root. So what is the link between these two things of roots with multiplicity and dominant roots? Well, it has been observed that for a large family of time delay systems, roots with high multiplicity are dominant. So when this is the case, we're going to say that we have the multiplicity-induced dominancy. So this means that if I have a root that has a very large multiplicity in a time delay system, this root is going to be the rightmost one. This does not happen always, but it happens for a very large family of systems. And so we're going to say that a family of time delay systems, depending on some parameters, satisfies the multiplicity-induced dominancy property, which I'm going to call MID in the sequel, if whenever I choose the free coefficients of the system to guarantee the existence of a real root of maximum multiplicity, this root is necessarily going to be dominant. And so this is a very useful property for the stabilization of systems with time delays. Because if I can choose my coefficients to place a root of maximum multiplicity with which is negative, a real root which is negative and has maximum multiplicity, this root is going to be dominant. So this is going to be the rightmost root in the complex plane. So all roots will also have negative real part, and so my system will be stable. So this gives me an algorithm to try to select parameters of a system in order to stabilize it. Now, the study of this property was first suggested in a book in the 1950s by Pinay, where he considers the question of minimizing the spectral system of some time delay systems, and he shows that he can do that if this property is satisfied, and he shows that this property is satisfied in two very simple systems. And since his works in the 1950s, there was a huge gap where this property was a little bit not so much studied, but people from control theory have recently realized how important this property is in the stabilization of time delay systems. And so since the late 2010s, we have some works that have proved this property for some families of systems here. So for instance, this work has proved it for systems of order 1. This has been extended for systems of order 2. In this work, this has been extended for systems with also with a first derivative on the unknown function y. This work considers a neutral equation. This one considers a general equation with a single delay. There's a work considering this multiplicity-induced dominancy property for complex conjugate roots. So instead of having a real root that has maximum multiplicity, you try to place a pair of complex conjugate roots. And in this final result, we consider the case where we have more than one delay. So I'm going to consider in the sequel of this talk is these three cases here, which present the results and some ideas of the proof and interesting connections with some other domains. So I'm going to start with this one, which is the general result for time delay equations with a single delay. So let's consider this equation here. So I have a non-delayed term here, which is of order n, a delayed term here, which is of order m, and m is less than or equal to n. So I can cover here both neutral and retarded cases. And in this case, the corresponding characteristic function is this quasi-polynomial here, this polynomial plus exponential minus s2 times this polynomial. And if you go back to the definition of degree of quasi-polynomial that I've given, you realize the degree of this is m plus n plus 1. So this is the maximum multiplicity a root of this can get. And what you can show is that a certain real number is a root of attaining this maximum multiplicity if and only if we have some relations satisfied by the coefficients of our system, the root of maximum multiplicity, and the delay tau, and of course, n and m. And the interesting part of this result is that if these conditions are satisfied, then necessarily this root here is dominant, so it is the rightmost one in the complex plane. So before going to the proof of this theorem, I just want to show an example of how this theorem is useful in control theory. So assume, for instance, that I have an equation like this. So this is just a damped oscillator. Okay, so here zeta is between 0 and 1. Omega is positive, and so I have here the equation of an oscillator with a control term u of t. If I do nothing, so if I take just u equal to 0, the characteristic function of this problem is just this polynomial here, which has two roots, which have real part minus zeta omega, And so in particular, they have negative real part. And so we know that the system is stable if I put u equal to 0, and now solutions converge exponentially to the origin. But the question is, can I choose u such that I converge faster? And let's see what happens if I choose u like this. So I'm going to assume that I can measure the state y instantaneously, but I cannot do the same for the velocity. I have to compute the velocity, and this takes some time, so I can only measure the velocity after some delay. Okay, so let's assume that I take u like this, an instantaneous measure of y, a delayed measure of the velocity, and also a delayed measure of the states. So if I do like this, the corresponding characteristic function is a quasi-polynomial like this. And you see that, in particular, I don't need an instantaneous measure of the velocity. And if I write down the conditions of the previous theorem, we realize that for us to have a root of maximal multiplicity at some value S0, my coefficients must satisfy this, and S0 is given by this. So in particular, this is a number that is strictly smaller than minus z to omega. So if we choose u like this, we're going to converge to the origin faster than if we choose u equal to 0. And the previous result tells us that this value here is the root with largest real part, and so this is going to give us the decay rate of solutions. And indeed, just a very simple numerical example here, these are the two roots of the polynomial that we have in the case u equal to 0. With my choice of u, I have a retarded system whose spectrum is represented here, and you see that I can move the spectrum to the left like this. And by doing simulations of solutions, we can see that in blue here, we have the solution when you take u equal to 0. And when I take my function u with my parameters chosen according to my theorem, I can make the solution converge to 0 much faster, which is sometimes desirable in control systems. Okay, so let me give you some ideas of the proof of that result. So we want to show two things. We want to show that we have roots of maximal multiplicity under some conditions, and that this root of maximal multiplicity is dominant. So the first thing we can do is just perform a change of variables that corresponds to a translation and a scaling factor in the complex plane that says that in the end, it's sufficient to consider the case where I want to place a root of maximal multiplicity at 0 and the delay is equal to 1. And so I have just two steps for the two things that I want to prove. Imposing maximal multiplicity, which is the easy step. Essentially, what you do is that we know that 0 is a root of maximal multiplicity if and only if delta and all its derivatives up to order m plus n are equal to 0 at 0. And this just gives me a linear system in the coefficient, which I can try to solve. This is just some long and tedious computations, but that we can do by hand in order to provide expression for these terms here. And the difficult part is essentially the dominance, and that's where when something somehow magical happens, when we choose the coefficients of the system in order to impose maximal multiplicity, we can prove that the quasi-polynomial that determines the behavior of the system has a very interesting factorization. It is factorized as z to the power m plus n plus 1. So here I have 0, which is a root of multiplicity m plus n plus 1. So I know that I can factorize by this term. And the remaining part has an integral representation here, which is t to the power m, 1 minus t to the power n, exponential of minus zt dt. And it turns out that this integral representation is nothing but a confluent hypergeometric function. A confluent hypergeometric function is a kind of special function which depends on two parameters a and b here. It's a function of the complex variable z, and it's given like this. So we have some constant factors here times an integral that depends on z, and you can recognize that up to choosing the good a and b is the same thing up to the change of sign in the z term here. So what I can do is that we want to prove that the root with largest real part of this function is 0. So all we have to do is to show that the roots, all roots of this have a real part less than 0. And for that, we can exploit some properties of confluent hypergeometric functions to prove that that his root is indeed strictly dominant. So essentially, we use some classical techniques developed by Hilde in a paper in the 1920s, so essentially 1 century ago, to show that indeed we have the required property for the roots of these functions. So now that the theorem is proved, I want just to give you some ideas of the extensions that we can show. The first one is what happens if instead of having a real root of maximum multiplicity, I want to place complex conjugate roots. So we did a study on that in a lower order case. So in the case of a second order equation with a first order delay, in this case, the degree of the corresponding quasi-polynomial is 4. And what you do is that we place 2 complex conjugate roots of multiplicity 2 each. And you can show that this is always possible if we choose the coefficients like that. And if we choose the coefficients like that, and we have these roots of multiplicity 2, these roots are necessarily dominant when these conditions are satisfied. So just to give a hint on the idea of the proof, in the case where I just want to place as roots 2 imaginary numbers, I theta 0 and minus I theta 0, well, what I can do is that I first consider the case where theta 0 is equal to 0. I know by the previous result that I can place a root of multiplicity 4 here, which is dominant. That is, all the other roots are here on the right half plane. And so the idea is that I want to take this root of multiplicity 4 and make it split into a pair of complex conjugate roots of multiplicity 2 each. And the question is, do I remain dominant? Do these 2 roots here remain the rightmost roots in the spectrum? And to see whether they remain dominant, well, if they lose dominance at some point, it's because a root has appeared here in the right complex half plane. And since roots are continuous functions of my parameter theta 0, this means that there are only 2 possibilities. Either I have a root that comes from infinity, meaning that the root tends to infinity if theta 0 tends to 0, or I have a crossing. And what I can show is that both situations are impossible. By providing some spectral bounds in the first case, we can show that roots cannot come from plus infinity. And by studying roots in the imaginary axis, we can show that I theta 0 and minus I theta 0 are the only roots in the imaginary axis. And so we cannot have this crossing because otherwise this would create a new pair of imaginary roots here, which is not possible. And just to conclude my last 2 slides, because I see my time is also almost over. What happens when you have 2 delays? Well, in 2 delays, we don't know too much how to proceed, except in the simple situation of a system of order 1 with 2 delays here of order 0, so a retarded type. So in this case, the corresponding quasi-polynomial is this, and the degree of the quasi-polynomial is 3. And we can prove that we have a root of multiplicity 3 at a certain real number S0, if and only if these 3 conditions here are satisfied. And in that case, the root is necessarily dominant, so it is the rightmost one in the spectrum. So what's the idea of the proof of this result? And I'll conclude with this slide. So without laws of generality, we can always assume that the root that we want to place is 0, that the largest delay is 1. I just rescale time in order to normalize the largest delay to 1. And so the smallest delay is going to be a number between 0 and 1. So in this case, if I just do these normalizations, S0 equal to 0, tau 2 equal to 1, and tau 1 equal to a certain parameter tau here, which is between 0 and 1, the conditions that I have here, if I plug them into the equation, I get this quasi-polynomial here, which can be seen as a function that depends on S, but also on the parameter tau. And what you can show is that as tau tends to 0, this quasi-polynomial here tends up to our normalization to this quasi-polynomial here, which is the characteristic function of a time delay system of order 2 with a single delay, which is equal to 1 of order 0, for which we know that we have the multiplicity-induced dominancy property. So we know that for this system, we have a root of the origin and several other roots that all have negative real parts. And as tau tends to 1, we have this equation here, and for this equation, we can prove that we also have a root at the origin of multiplicity 3, so the same multiplicity as for this one, and all other roots lie in the imaginary axis. So the question is, when tau moves from 0 to 1, does this root here at the origin remain dominant? Does it remain the rightmost one? So the question is also, how do the other roots move? So how does the red root move here to the blue root? It could move like this, or like this. So if I denote S of tau, the function that to each tau associates a branch of a certain root, we can prove that this branch is always going to be simple, that it remains bounded as the delay tends to 0 or as the delay tends to 1. And you can prove the following properties. So if it crosses the imaginary axis at some point, then necessarily the derivative is positive, meaning that the derivative of its real part is positive, meaning that it has to go from the left to the right. So it cannot cross back. The situation that I have drawn here is impossible because we cannot cross back. Okay, so the only possibility is that if I lose dominance at some point and I have a root that crosses, since they remain bounded and they cannot cross back, the only possible situation is that they converge to a blue root as tau tends to 1. But by studying the derivative of S and the second derivative of S at 1, we can show that roots necessarily converge these blue roots from the left and not from the right, meaning that the situation that I just described is also impossible, and you cannot have roots here in this right half plane. So all my roots are here on the left. And so we have the dominance of these roots for all parameters between 0 and 1. So this is what I wanted to say, and I think my time is over anyway. So I thank you very much for your attention.